Welcome back. This is going to be video lesson number 3 for the mathematical induction. And up to now, we've sort of given ourselves the basic conceptual stuff that we need to be able to not only sort of know what we're doing when we're doing mathematical induction, but also the basic setup that we need, namely that you need to have a series for the mathematical induction to work. So what I'm going to do in this video lesson is just go over a quick intuitive example of how this will work by showing how you can claim that all of the sentences of SL have the same number of left and right parentheses. And I'm not going to go into too many of the details here. The book is really good at making everything, laying everything out in a really detailed way. So what I want to do here is just give you more of the intuitive feel for how this proof will work, to sort of, which you can then go back and look at the book to see the elaboration of it and some of the more details you need. So this is going to be the intuitive version for proving the following claim. So the claim we want is that every sentence of SL has the same number of left and right parentheses. Okay. And here's how we're going to do that. So this is our claim. Every sentence of SL has the same number of left and right parentheses, right? So the number of left parentheses is equal to the right parentheses. And actually, that's maybe a better way of having to do it, is that the number of left parentheses equals, let's do that. So we'll just have I'll have LP as left parentheses, okay? So the number of left parentheses equals the number of right parentheses. So this would be a nice shorthand. So left parentheses, right parentheses. And so this is how we're going to prove a claim like this using mathematical induction. So the first thing we write down is, we indicate that we're going to provide a proof of this claim. And we're going to, point out, we're going to say, okay, we're going to do this by mathematical induction. Right, so this mathematical induction, I'm just going to abbreviate this as MI. And so here's how we do it. We need two parts for this. You need the base. Oh, there we go. And we're also going to need the inductive step. And I'll write it down here for now. But I might have to erase it and move it, but we'll just keep it here so we know. So there's going to be two parts. We're going to need the base and then the inductive step. And I think the book calls this the basis clause. And the basis clause, what you're going to do here is show that it holds for the sentences that have zero connectives, right? So if you recall, when we were building up our sentences, we had A and we also had B, and in stage one had all the atomic sentences, right? So all the atomic sentences, those are that group of the atomic, the group of atomic sentences, they're the ones that have the base case. So those are the ones that we talk about first. And here's how the proof intuitively go. So we have the claim that we need to establish this claim, right? So the claim is about every single sentence of SL, right? That every sentence of SL has the same number of left parentheses as the number of right parentheses, and vice versa, so that they're equal. So we're going to show first that this statement is true, at least for the sentences that have zero connectives in it. So base, so this is sentences with zero connectives. right? So you can see that the way this induction is going to work is we're going to show that it holds for 0, and then we're going to show that it holds in the inductive step. We're going to show that if it holds for k, then it will also hold for k plus 1, where k here is the number of connectives that we're considering. And in fact, we'll actually do it for all the sentences up to k. So the actual mathematical induction, right? So the reason why it's called mathematical induction is because we're still using numbers to actually do the induction. It's just what the number is representing is the number of connectives in our sentence. So our base case is going to be the group of sentences that have 0 connectives. And the idea for the base case is just, this is almost going to be trivial, so the base case is in many ways the easiest one to do. We'll just point out to the fact that any atomic sentence, any sentence with 0 connectives is going to be atomic. So we know that, so let me just scratch this out. Any sentence with 0 connectives is going to be an atomic sentence. So that's our first step. And then we know that atomic sentences have 0. So atomic sentences have 0 left parentheses and 0 right parentheses. Let me just erase this inductive step right here. And we know that 0 equals 0, right? So you can actually just write hence atomic sentences, I'll just abbreviate that. Hence for atomic sentences, the left parentheses equals the right parentheses. Tricky. The number of left parentheses equals the number of right parentheses. Okay, so that's our base case, right? We start with a sentence that has 0 connectives. We know that any such sentence is going to be atomic. And we know that an atomic sentence has 0 left parentheses and 0 right parentheses, right? So if you look at the definition of recursion that we gave, which is up here, every sentence letter is a sentence, and a sentence letter doesn't have a left and right parentheses. So trivially, it has 0 left parentheses and 0 right parentheses. And then since 0 equals 0, we know that the number for left parentheses is equal to the number of right parentheses. So that's our base case. Now we need to talk about the inductive step. So normally you would write the inductive step here underneath the base case, but since I'm running out of room here, I'm going to erase the base case, and then I'm going to just assume that we've shown the base. Right, so I'll just write down here that we've done the base case, put a check mark there. Now we're going to the inductive step. And this is the one that's a little bit trickier. Okay, so this is going to be a conditional. So remember when we had the intuitive way when we had the analogy of the dominoes, we said that if something holds for the kth domino, then it'll hold for the k plus 1 domino, right? So if we show that if all of the dominoes up to including k have fallen, then k plus 1 will have fallen as well. So what we're going to do is make the following claim. So let me actually just go back to show you what the inductive part is going to be in the actual text. So here, this is the second premise of the argument that is presented in the textbook, and this is what I'm talking about when I'm saying that the inductive step. So what they're pointing out here is that, look, if every sentence of SL with k or fewer occurrences of connectives have the same number of left parentheses as right parentheses, and vice versa, then every sentence of SL with k plus 1 occurrences, so let me put this up, of connectives is also such that the number of left parentheses equals the number of right. So this is the inductive step, and what you actually have, what you can do is you assume the antecedent, and that's called the inductive hypothesis, right? So you're going to assume that every sentence of SL with k or fewer ... So let's write that out. So the inductive step has an inductive hypothesis, and I'm going to put this in a different color here. So our inductive, and it's good to write this out. This is what I usually do. So the second part of the proof is the inductive step, and I'm going to write out what my inductive hypothesis is. And the inductive hypothesis says that every sentence with k or less connectives are such that, so ST here is just such that the number of left parentheses equals the number of right parentheses. So that's my inductive hypothesis. I'm going to assume that all the sentences up to k or less, all the sentences that have k or less connectives are such that they have the same number of left and right parentheses. In the same way as, when I had the case of the dominoes, I assumed that all the cases up to k have actually followed. Then there's sort of two ways of breaking this down. So you're going to have case 1. You're going to do, we're going to do proof by cases now. We're going to have a case 1 and we're going to have a case 2. In case 1, what you have is the addition of the negation. All right, so we're going to assume that P is a sentence that has k or less connectives. And now we need to see what happens when we add negation. And intuitively, so if you think back to the rules that we had before, so we go back and we appeal to the syntactic way we built up our sentences, we said if P is a sentence, then not P is a sentence. Not P doesn't add any extra left or right parentheses. So in the case when we're introducing the negation out in front, we don't add any extra left or right parentheses. So you can say, so in the case 1 with not P, no additional parentheses are added. And then, since the inductive hypothesis says that the number of left parentheses equals the number of right parentheses for P, right? So we're assuming that the left and right parentheses equal for P, then not adding any extra parentheses will mean that the number of left parentheses equals the number of right parentheses. There we go. In this case, in the case of adding negation. And for what it's worth, I'm doing this in this really messy, sort of intuitive way, and the book has laid it out in a much neater and clearer way. And we're, in class I'll go over another example to sort of give you an idea of what is expected and how to use the mathematical induction. I'm just trying to do this for you somewhat quickly so that you can see intuitively what's going on. Okay, so that'll be the case 1, and then we also have to show another case, case 2. And in fact, what you can usually think of is the number of cases you need is at most the number for all of these. So we just showed that, look, if we assumed that P has the number of left and right parentheses in P are equal, then that holds for not P. And the number of cases you need at most are for all of these different ways of constructing sentences, right? So you need to show that it holds for P and Q, that it holds for P or Q, if P then Q, and if P if and only if Q. But sometimes you can take a slight shortcut, and that's what we're going to do in this case. Since we know that all of these are the same in that the only way that they differ is the connective that they put in the middle, we can actually just talk about case 2 and sort of reason over all of these 4 cases all at once, because effectively what they're doing is adding the same number of parentheses on either side. So our case 2, let's do this. Our case 2 is going to apply to the conjunction, disjunction, the conditional, and then the material conditional, and then the biconditional. And the reasoning is going to be similar, right? We have that by the inductive hypothesis, right? So by the inductive hypothesis, oh man, that's not good at all. There we go. By the inductive hypothesis, we can assume that P and also that Q have the number of left parentheses equal the number of right parentheses. That's what we get to assume by the inductive hypothesis. Now we need to show that under that hypothesis that by the addition of constructing the new sentences using these connectives with P and Q, that the resulting sentence will also have the same number of left and right parentheses. And so hopefully you see that intuitively, right? I mean, each of these cases, all we're doing is adding one left parenthesis and one right parenthesis, and we're doing that in any of these cases. So what we can do is say, if we said it by conjunction, well, then the number of left parentheses for the resulting sentence, suppose the number of left parentheses is, well, actually no, I won't give it a number. I'll just say that the resulting sentence here will be LP plus 1. Similarly, the number of right parentheses will be the number of right parentheses before plus 1. So now it's easy to see that, look, by simple addition, by simple arithmetic, this addition of one left parenthesis and one right parenthesis won't actually change this equality, right? We'll maintain that equality. And so that's the intuitive thing that they're actually doing in this text, right? So they're doing the inductive step. Sorry, this is actually down here, right? So the inductive step, what they're showing is that the number of left and right parentheses is the same for all of the cases, right? For the case of the negation and the case for the conjunction, disjunction, and conditional. Okay, so let me stop there. So this, again, was just sort of a quick and intuitive way of getting a feel for what it is that they're doing in the text. And hopefully by going back to the text, you can now get a feel for the details that I've kind of left out here. And during class time, we're going to go over another example of using mathematical induction for proving things of sentences of SL.